I put also some other in fact slides which explain in more detail all the explanation that I explained before. You can see them if you are interested. Here you can see our boxes and so on, converting our boxes in each steps, and some example of one of box in one algorithm, and also some numerical examples. Okay, you can read them if you are interested. If not, I explained all of them in more details. The last part of our in fact lecture about this algorithm is avalanche effect. In avalanche effect, in fact, with a small change in our plain text or in our key, we will have significant change in the final result, in fact in our cipher text. To having this feature, it is evidence that the high degree of diffusion and confusion must be considered in an encryption algorithm, which is desirable property for any in fact effective and secure encryption algorithm. We have this avalanche effect in this algorithm, which means that changing only one bit in our plain text, which will affect a big difference, something like 34 bits in the cipher text in average, sometimes for instance 32 or 33, and also changing only one bit in key will be affect a big difference, something around, not exactly equal to 35 bits in the cipher text. Sometimes it's important to know that this number is not an exact number. Sometimes we have, for example, 32, 33 or something around that on average. Okay, this is desirable for any algorithm which will be considered as a secure algorithm. Here you can see an example of the avalanche effect. In fact, in this table you can see in two rows two plain text. The first plain text and the second are exactly the same, only one bit are different. The first one is starting with 0, and the second one is started with 1. As you can see here in this column, you can see the number of bits that are changed after each round and after each step. And you can see finally we have something like 32 bits of difference. This is avalanche effect in plain text changing. Again, the same thing will be happened by changing a bit change in our keys. Again, after the last part, you can see here we have something around 30 bits difference and maybe more here. At the 8th round, we have 32 bits difference from the first steps. Okay, and as a numerical example, as you can see here, we have two plain texts, plain text number 1 and plain text number 2. After in fact executing this algorithm, the ciphertext will be different in 32 bits. And in the other example, we have key number 1 and key number 2, which are again different between only 1 bit. This one 0 is in the second is changed into 1, and the ciphertext will be different in 30 bits, which is enough for a secure effect and a good efficient algorithm. Okay. Anyway, using several rounds in this algorithm to make it more confusing and considering many different security considerations, it doesn't make this algorithm secure enough. For instance, a brute force attack for this only can be in fact done in even when you consider a large key space size, for instance 2 power 56. And it has been shown that the differential cryptanalysis is possible only when you have this number 2 power 47 samples of plain text and ciphertext. You can break this attack. And also by linear cryptanalysis, only having 2 power 43, some attackers have shown that this can be broken by non-plain text attack, as we described in the previous lectures. Hence, in fact, they decided to provide more secure algorithm. In fact, they said that we can use or we can implement this algorithm multiple times using multiple keys. We have 2 disks and also sometimes 3 disks to reinforce this algorithm. Okay. In 2 disks, consider that we encrypt our plain text 2 times with 2 different keys, key 1 and key 2. What do you think about that? If it is enough, in fact, it means that you increase the key length 2 times rather than the in fact original length, but it is not enough. Okay. And again, 2 days was broken with an attack which called meet in the middle attack. Because we don't have enough time, I will skip this part, and you need to read it yourself after. Then we can consider 3Ds. 3Ds can be considered only with 2 keys, as you can see here. In 3Ds with 2 keys, in fact we have 2 keys, key number 1 and key number 2, and we use, as you can see here, in each step for encryption. First of all, we encrypt the plain text with the first key. Then we use the decryption algorithm with the encryption key 2. Then we encrypt the results of the previous step with the first key, and we obtain our ciphertext. And to do the decryption, as you can see in this diagram, we need to do the inverse methods. First of all, we decrypt the ciphertext with the first key. Then we encrypt the result with the key number 2, and finally we decrypt the result with the key number 1. Okay, here you can see the implementation or the formula of our 3Ds. It is clear that if we consider the key number 1 and number 2 to be the same, we will have the same general Ds, not 3Ds, 1Ds. Okay? Till now, in fact, no practical attacks have been shown are 3Ds. But to provide more secure way, it would be better to consider 3 different keys in 3Ds. In fact, some interesting applications adopted 3Ds with 3 keys like PGP protocols, which are widely used.